Okay, so we're live with 52 weeks of AWS. I'm continuing to cover the AWS machine learning certification. Last week, we were able to cover half of the pipelines documentation, but there was so much material, I couldn't fit it in 30 minutes. So I'm going to go for part two. And this is really an important topic. Excited to get in and get started with this. So what I'm going to do is I'm going to get right into it and share my screen here. Here we go. And let's proceed and dive right into this. So, in a nutshell, in fact, let me just change one thing though, real quick, which is before I get started. Let's see here. Presenter view. Here we go. Yeah, let me just change this one more time and set up a screen share. We'll do that. Here we go. Okay, so we're back here, and we're going to plan for missing values as really the last place that I left off. And I'm going to talk a little bit more about this topic and get into the weeds a little bit about it. But really, in a nutshell here, when you're dealing with missing values, you'll see this with pandas a lot. One of the easier ways to deal with it is just drop all of the missing values. Now, there's some downsides to this because if you do use this approach, for example, that you could potentially get rid of a lot of data. So maybe you want to do it at a more granular level. So you could only drop values on, let's say, a particular column that had missing values. That's one approach to do it. You could also drop maybe a subset of the data as well. So there's some approaches to potentially doing it in a less dramatic way, especially if you're not getting the accuracy that you want. Another way that you can handle missing values is to impute the missing value. So first you figure out why there's missing data, and then you would impute that missing data with univariate or multivariate. So basically adding data for a single row of missing data, that would be univariate. For multivariate, it would be adding data for multiple rows of missing data. So in the case of this example here, I would say from scikit-learn.preprocessing import imputer. So you'll see this with the scikit-learn library. Obviously, it won't work on big data, but for smaller data sets, the preprocessing, you could go in here, just import it, import NumPy as NP, make an array, and then go ahead and build out a strategy. For example, a mean strategy, right? So take the average and then put that average anytime you find there's a missing value, and then fit it and then transform the data. So a pretty reasonable strategy as well to attempt when you're looking through missing values. Now, outliers are a really interesting problem that happens in data science. And in fact, this is really the one of the bigger issues of our time, right? Where, I think an outlier on one hand does provide the whole picture, right? Like you can see things here like, hey, what's going on? Like, why is it that the majority of items are in this one region? Like in the case of a traditional linear relationship, you'll see all of the points, the XY coordinates are kind of clustered in a pattern. But then when you see an outlier, it's like, well, what's going on? Now, if you're a conspiracy theorist, you'll do the opposite of data science, right? And that's really what a conspiracy theory is. It's taking the outlier and throwing away all of the data and only making predictions based on an outlier. So in a sense, anytime you hear about any kind of a conspiracy theory, it's anti-data science, right? I think that's the best way to think about it. Now, it doesn't mean that there's not something interesting going on. And it could be that maybe there's a data collection error, or there is a new population maybe that you want to look at. But it is important to be, first aware of it, but then figure out how you want to deal with it. The thing you definitely don't want to do is throw away all the good data and only look at the outlier and potentially, create predictions based on that. Now, in terms of finding outliers, there are some really neat tools that allow you to find them. For example, a box plot, so you can show the variation and the distance from the mean. And so box plots are one of the premier tools really for dealing with outliers. A scatter plot as well is a really good tool to show outliers. For example, the relationship between alcohol and sulfates in a collection of wine, right? You'll see these outliers. So what do you do in a nutshell? So one, you could delete the outlier. So if the outlier is based on artificial error, right? So again, if it's a data collection error, there was a human that created a bad entry into a database, like you don't want that, right? That's something you want to actually remove. You could transform the outlier. So another thing you could do is reduce the variation that the extreme outlier causes and the influence on the data set. So you could do some kind of a transformation, like logarithmic transformation, for example. The other thing you could do is you could impute a new value for the outlier. So maybe the mean of the feature, for example, and impute the value to replace that outlier value. So there are some different ways, and it's a nuance, right? It really depends on the data set. That's why you need domain experts. You need also statistics experts. These are some of the things that make data science difficult. So for feature selection, there are a few different ways to consider dealing with feature selection. I mean, one of the ways that you could deal with feature selection is to use statistical methods. For example, you could go through here and figure out the appropriate features based on, things like correlation with the target. This is a very common way to do it. This is why you see correlation heat maps. You can do a wrapper method as well. And this would be measure the usefulness of a subset of the features by training a model on it and then figuring out how successful it is. The filter methods are typically faster and cheaper than wrapper because you don't have to train the model over and over and over again. But wrappers are best at finding the subset of the features with a risk of overfitting compared to using subsets of features from filter methods. And embedded methods are algorithm specific, and maybe they use both of those techniques. So filter method is a proxy for using an actual model's performance, and they're able to compute and capture the usefulness of the feature set. So a good example would be Pearson correlation coefficient. This would measure the statistical relationship or association between two continuous variables. There's also LDA, or linear discrimination analysis. You would use this to find separate classes. There's analysis of variance, or ANOVA, and you could figure out the differences between groups of means in a sample. There's also chi-squared, right? A single number that tells you the difference between observed counts and expected counts if there's no relationship that exists in the population. And so they're less computationally expensive than wrappers, but they produce a feature set that's not tuned to a specific type of a predictive model. So a feature set doesn't contain the assumptions of a prediction model. Therefore, it's more useful to expose the relationships between the features. So a wrapper method would use a predictive model to score, feature subsets. A forward selection would be if you're starting with no features and you would add them until the best model. A backwards would be starting with all the features, drop them one at a time, and select the best model. So really, there's a couple different approaches when you're going through and you're figuring out this wrapper method. So embedded methods would combine the qualities of filter and rapid methods, and they would be used potentially from an algorithm that has this built-in selection method. Some of the most popular examples are lasso and ridge regression, which have a way of penalizing functions to reduce overfitting. So if you were, for example, dealing with a data set with a lot of outliers, potentially this is one of the ways that you could deal with it. Now let's go ahead and talk about training next year. So if we dive into models and training it with data that you've pre-processed here, one of the things to be aware of is that there are different file formats for machine learning: CSV files, record files, text files, JSON files, protobuf record files. There's a lot of these kinds of files, and so it's important to know what file format you're dealing with. Some of the algorithms in SageMaker may actually not work unless the data is in a particular format, and actually SageMaker algorithms themselves will potentially ask for a very specific format. And so this is one of the things that is really important to be aware of. And with SageMaker, typically you want to use the optimized protobuf record IO format for training the data. In that format, SageMaker would convert each instance in the data set into a binary representation as a set of 4-byte floats, then that it loads into the protobuf values field, and this then loads the protobuf values field and enables you to take advantage of the pipe mode, right? And so pipe mode would allow you to stream the data back and forth with S3. And so this is a key feature here, is that S3 has this ability to do, really incredible disk IO and storage and compute. And so if you're able to pipe into it, you're able to get very, very fast training as well. And so this is something to be aware of when you're dealing with a different type. Now, the target variable in your data set should be the first column on the left, and your feature should be the right of the target column here. And so when you use a CSV format, use the first column as the target column. That's a kind of a tradition. Now, when you're dealing with the same data, it can lead to overfitting, and this is where you split the data, right? So when you are overfitting your data, it's important to be aware of the fact that you want to really be aware of memorizing the data too closely, or you will overfit it. And so you want to have a training that is able to generalize to new sets of data. Really, that's the idea here between splitting the data. And so the traditional way to deal with this is 80% of the data is training data, 10% of the data is the validation data, and 10% is the test. So how does this work in practice? So the holdout is when you split your data into multiple sets. The training data is the features and labels for the algorithm that you're going to use to produce the model. So this is the most important part, right? This is where you're getting the signal. But then with the validation data set, this is where you might notice that you'll want to tweak or tune or change things. And when you're ready, you then run the test data set, which only has features because you want the labels to be predicted. The performance you get here with the test data set is what you would see potentially in production. And so a common split when you use the holdout method is as following: 80% for the training, 10% for validation, 10% for the test. If you have a huge amount of data, you could split it into 70% training, 15% validation, and 15% split. So it's good to know like a formula for what has really been demonstrated to work best, and this holdout method is an approach that works well. Now, for a small data set, there are some problems, and one of the ways that you can account for this is this technique called k-fold cross validation. So you can still use a lot of the data, but really what's happening under the hood here is that you're able to not have to worry as much about you trained on potentially a non-random component of the data. And so in this case, because you're sampling many different subsets of the data, you don't have to worry about, oh, I just happened to train on like a part of the data that wasn't necessarily as generalizable as a random sampling of the data, right? So this is what my intuition behind why you want to use cross-fold validation is. It really makes a truer random sampling of the data because you're taking many different samples of the data and then applying the training across this. So one of the things to be aware of is one of the problems with splitting your data is that if the data is in a specific order, it can lead to biases in the model. And so this is, again, why randomizing your data set before splitting typically is sufficient, and many libraries will let you do that. But with a smaller set, you may want to use something called stratified sampling to ensure that the training and test sets have an appropriate number of percentage of samples of each target class as the complete set. And so you can do this with scikit-learn. You could say from scikit-learn.model selection import train test split, and go ahead and select this stratify. And so this is where things can get into some really nitpicky weeds here. And it is important to kind of know what's happening underneath the hood when you're training a model. So when you do get to the point where you're training a model with SageMaker, SageMaker has ML algorithms that are optimized for speed, scale, and accuracy. They've got built-in algorithms, SageMaker frameworks, also custom frameworks, and the marketplace. A few things to be aware of is that you can interact with SageMaker in the console, the CLI, Python Notebook, Python SDK. It also deals with frameworks like Apache MXNet, TensorFlow, PyTorch, Chainer, and also custom frameworks as well can be used. So what are some of the built-in algorithms? And why would you want to use them? I think one of the big things to be aware of is that they're optimized for high performance and they're scalable. And I think this is really the advantage of something like SageMaker, is that they're built for doing huge distributed training on data sets for classification. We've got XGBoost linear learner for quantitative. We have XGBoost linear learner for recommendation. There's factorization machines for unsupervised. There's k-means clustering, and then PCA, or principal component analysis. And then these specialized kinds of algorithms for like processing images or doing deep learning, sequence to sequence or neural topic modeling. So let's take a look at some of these algorithms first here. We have XGBoost, which is a popular and efficient open source implementation of the gradient boosted trees algorithm. The gradient boosted is a supervised learning algorithm that attempts to accurately predict a target variable. It can do this by combining an ensemble of estimates from a simpler, weaker models, and it has done very well in competition. So XGBoost is definitely one of these algorithms that you'll find that performs generally very well for many problems. The Amazon SageMaker linear learner algorithm is a solution for both classification and regression. And the algorithm is really well suited for continuous objectives. And it's a huge increase in speed over naive hyperparameter optimization techniques. K-means is an unsupervised machine learning algorithm. So it means that like there are no labels in the data. You need to discover about this. And so you would define the attributes you want the algorithm to use. For example, I do a lot of k-means clustering, and sports would be a great one. For example, if you wanted to find the best players in the NBA, you could look at blocks, rebounds, assists, in turnovers, for example, and you could use that to cluster and figure out who's the best players in the NBA. To train a model in SageMaker, you could create a training job. And really the way it works here is that you have the training bucket, which is the S3 bucket, and then you have your code that would go through and do everything. You would have your compute types, CPU, GPU, memory, whatever it is you're using. And then you have the target, which would be where you'd want things to actually get put to, like where the model would go to. And then the ECR, or Elastic Container Registry, is where your training code is actually coming from. Okay, let's talk about hosting and using a model with SageMaker. So one of the things that is important to be aware of with SageMaker is that there's this life cycle, right? There's training a model, tuning a model, testing a model. And so after you've trained, tuned, and tested your model, you're ready to deploy it. And so you might think they're looking at the phases in the ML pipeline that are out of order. And so deployment for testing is different from production. And really, SageMaker gives you the whole pipeline in order to do a deployment that can handle, let's say, tens of thousands of requests. So you can deploy your model in a couple different ways. So for a single deployment, you can use the SageMaker hosting service, and you can deploy it to different compute instances, and you can call the API behind it. if you want to predict, let's say, an entire data set, let's say you want to do a credit scoring operation for mortgage lending or something like that, you may want to do a batch transformation. And what that would mean is that just maybe every night you go through and you take your entire data set, you score everybody, you give them credit scores, and then let's say you put it into a data warehouse so that you know what it is you're going to offer a particular person when they apply for a loan. The goal of the deployment phase here is to manage an environment to host models for providing inference, for securely, creating predictions here, and if necessary, you're going to have to retrain your model because a newly deployed model has to reflect the current production data. So this is where the drift comes in, right? Where you're going to need to deploy your model more than once. It's not going to be just you have this one model, you deploy it, and you're done. In a real world, you're going to have to continuously deploy this model. So for the high availability and redundancy, you can deploy your model to the ML instances across different availability zones. And then SageMaker would take care of the rest. And your application has to include an API to call the endpoints to achieve low latency and high throughput in inference. So this is where it really does pay to have some expertise with AWS architecture. Like in the case of knowing about availability zones and regions in AWS and auto scale groups, this is where these things start to come into play here. But SageMaker really is optimized for doing scaling your code inside of a deployment. Now, to create an endpoint is actually pretty easy. You can do it in code, right? You can just say, for example, XGB model deploy, and then you put in the instance type, which could be a CPU or GPU instance type, and then you put the initial instance count as a variable and select how many. You also could do multi-model endpoints as well, and they can have the same serving container that has multiple models inside. And that's a way to actually save cost, which is kind of an interesting technique. And so when you deploy your model into production, you can also make predictions on new data. So consistency is important, and you're going to need to ensure the same data processing steps you are used in training apply to each inference request, or you could get incorrect prediction results. So by using an inference pipeline, you can reuse the data processing that was applied in model training. And because SageMaker is a managed service, the inference pipelines are completely managed for you. And when you deploy it, the service installs and runs the sequence of containers on each instance. And additionally, the sequence of feature processing and inference runs with low latency because the containers are co-located on the same EC2 instances. All right, let's talk about how you can evaluate a model success. It's one thing to train the model, it's one thing to put the model in production. It's another thing, is it even doing anything, right? Is it helping my business? So after you train and tune your models and decide which model is the best for production, you're going to need to evaluate your model. Because these feature instances have unknown target values, you're going to have to figure out how to perform on data for which you know the target answer, and then use that as a proxy for future performance. And this is why you want to hold out a sample of the data for testing purposes. And so what would be your success metric? For example, is your business problem that you want to predict fraudulent credit card transactions? That becomes a model metric. And then you have to actually tie that back to the real world, right? Am I actually reducing the fraud claims? If I'm not, then my model is basically not working, right? Like you can have the best deployment, you can have the best model metric, but ultimately it's got to map to the real world. And I think we're seeing this quite a bit in terms of companies that are doing machine learning, is they want to make sure that they've actually got this solved. And so let's go ahead and take a look at how this would work. So let's take a specific example here. If you have a simple recognition model that labels something as a cat or not a cat, after the model is trained, you can use the test data that you had to perform a prediction, and this will help you evaluate it, right? So you would go through and you would do a prediction, and you would create a confusion matrix that shows like my accuracy of whether it's able to successfully test whether or predict whether something is a cat or not a cat, and when did it get confused. So in a confusion matrix, there's a few things that, and this always does confuse me, is there's the terminology is can just kind of wrap my head around, is there's the true positive, right? This is predicting a cat and it was a cat. There's a TP. There's a false positive, which is you predicted not a cat, but it was a cat. And then there's false negative, FN, which is predicting a cat and it wasn't not a cat. And then there's true negative. It predicted not a cat and it was not a cat. And this is also domain specific, right? In some cases, it doesn't matter as much about one of these metrics, but in some cases, it's really important to be accurate. So a good example would be COVID testing, right? When it first was a pandemic, you don't want to tell someone that they don't have COVID, like a false negative. It predicted, I guess in this case, a false positive is you don't want to tell someone they have COVID and then they actually do have COVID, right? That's the worst case scenario. Would be a false negative, right? Is you basically say, oh, yep, you're good, but then it turns out you're not good, because then you could spread, right? So you would want to be very, very accurate in that particular test. But again, it's domain specific. So what model is better? A confusion matrix from two models that use the same data. How do you pick it? It's difficult to look at a couple charts, but you could try different models, and then you got to calculate more metrics. And so you could look at things like, the first metric is sensitivity, and this is referred to as the recall, the hit rate, or true positive rate. This is a metric that's a percentage of positive identification. So in the cat example, it's percentage of cats that are correctly identified. To calculate sensitivity, you take the number of true positives, positive identification of cats, and divide that number by the total number of actual cats. So 60% of cats were identified as cats. The specificity is referred as the selectivity or true negative rate. This is the percentage of negatives that were correctly identified. In the cat example, it's the number of images that were not cats that were correctly identified as not cats. To calculate the specificity, you take the number of true negatives and divide that by the total number of actual negatives. In this example, that value is the number of not cats that were correctly identified divided by the total number of actual not cats. And so in this case, you would have to, again, pick the metrics for each model and decide what it is you're going to do based on that results. Classification models are going to return a probability for the target. So this is the probability that a value is between 0 and 1. And convert that to a class, you have to determine the threshold to use. And so you might think that maybe it's 50% is a good one, but it has a huge outcome on basically how sensitive something is. And this is where you get into ROC graph, which is the receiver operating characteristics. And so ROC is basically calculating the sensitivity or true positive rate against the false positive rate. So you want to basically figure out where do I care about being the best at, and it could be, again, specific to the business case that you're working on. Again, going into something like COVID-19, you want to be really, really careful about telling someone that they don't have COVID-19 and they do. So maybe you want to give up, maybe telling people, being accurate about when they don't have it. Like, you're okay with giving up some of that. And so in the case of AUC-ROC, it's easily to compare one metric against another metric. And that's really what the area under the curve does. And so with the 4 numbers from the confusion matrix, you can calculate the model's accuracy, which is known as the score. And the accuracy is a widely used metric for classification, but it does have some limitations because it's less effective when your data set has many true negative cases, for example. And so that problem can lead to ensuring that the metric you choose aligns with your business goals. So you can't just say the model's, this is the score and it's good to go. You need to actually look at it and decide the thresholds that correctly align with your business goals. Now, regression problems, in this case, you can use a common metric called mean squared error, or MSE. It's commonly used, and it's really the idea here is to figure out, how much error you have in your particular model. Now, if you've trained your model, performed a batch transformation, and calculated the metrics, you can use these to tune the model and figure out, basically how to make it better. Okay, let's talk about hyperparameter tuning now. So one of the things that is important to be aware of about hyperparameter tuning is you can think of this as a knob that you would tune the machine learning algorithm to really improve its performance. And so one of the ways that you can actually use hyperparameters is you can actually go through and figure out these different approaches. For example, with model hyperparameters, there are neural network-based models that require you to define an architecture before you can start training them. And with computer vision problems, there are additional attributes that must be defined, such as filter size, pooling, and the stride or padding. The other is optimizer hyperparameters, and these are ways that you would learn on the data, and these could be optimizers like gradient descent, stochastic gradient descent, and these use momentum like Atom, or initialize the parameter weights using methods like Xavier initialization or He initialization. The third kind is data parameters, which relates to the attributes of the data itself. And these include things like data augmentation techniques like cropping or resizing for image. So how do you tune the hyperparameters? You could do it manually, right? And this would be like a Kaggle, Grandmaster or something like that. Or in my opinion, probably you don't want to do this. You actually just use a tool like SageMaker and you do automatic hyperparameter tuning. You set up a job, it goes through, you tell it what the metric would be in the case of, let's say, a Gaussian process regression to predict which hyperparameter values are most effective. You could use Bayesian optimization to balance exploring the hyperparameter space and the values. So really, basically, you can fill out optimization algorithms that pick the hyperparameters for you, which I think is, for most business problems, is the correct approach. So with automated hyperparameter tuning, you really don't care about it. You just want to get basically the best objective metric, and you don't care as much about the very specific hyperparameters you're tuning. But it is important to know that just because you can do it doesn't mean it will improve your model. So tuning doesn't always improve the model. So that could be a computational expense that you want to be careful about. So what are the best practices? A few different things. Limit the number of hyperparameters is one. The range of values for hyperparameters can significantly affect the success of optimization. If you have more hyperparameter tuning jobs concurrently, you can get a lot done, more work done quickly, but the tuning job improves only through a lot of experiments. So running one at a time might be the right way to go. And when you're training a job on multiple instances, the hyperparameter tuning takes the last metric. And so you should design robust distributed training jobs. And during hyperparameter tuning, SageMaker attempts to determine whether your hyperparameters are log scaled or linear scaled. And it might take some time for SageMaker to discover this. So really, that's in a nutshell, the hyperparameter tuning. And maybe we'll wrap this up with SageMaker Autopilot. And one of the things that it can do is it can analyze data, select appropriate features, and then train and tune the model. This service doesn't mean that you don't need to pre-process the data, but it can help you with feature selection and model tuning. And so that's another thing to be aware of. So not only are there automatic hyperparameter tuning that you can use, but also automatic machine learning that you can use as well. So really, that's a very, very deep dive over some of the features over last week and this week of SageMaker. And I think the best way to deal with this is really to get into SageMaker and play around with it when you get a chance. All right. Well, that's it for me this week. And next week, we'll continue to go through the AWS machine learning certification material.